Today I'll talk about Hagen-Poiseuille equation, and also I'll show you how to derive Hagen-Poiseuille equation by using force balance, and I also show you what will be the shear stress distribution in a circular pipe. So now first we consider the flow is steady, laminar flow of incompressible Newtonian fluid through a cylindrical pipe or circular pipe. Now here fluid flow is happening in that circular pipe. Now first consider one cylindrical fluid element. Consider a horizontal pipe of, so here in this pipe radius is r, and a concentric cylinder fluid element with radius r and length del L within the pipe as shown above. So this is the cylindrical fluid element, and radius actually taking from that center line, that is r, and pipe radius, circular pipe radius is capital R, and that fluid element length is del L. Now force acting on the fluid element. So one pressure force is acting, the force acting on the fluid element is the pressure force and the viscous force. Now in that section, left hand side of this fluid element, the pressure is acting. So that pressure we can easily calculate, that is pi r square into p, and other side of the element, that pi r square p plus del p is acting. Why minus sign? That is the opposite of this. So pressure is acting in that side. Pressure is, we know that inward force by area. So in that area, so inward force is applied. So what is the inward force? Force is pi r square into p. Here also inward force, as the direction is opposite, so minus sign is there. So pi r square p plus del p. And that surface, that shear stress is acting. Shear stress is acting on the surface. Now that is also called viscous shear force. The viscous shear force acts on the cylindrical surface due to the viscosity of the fluid, and the shear stress tau is proportional to the velocity gradient, so that is du by dr in the radial direction, and the force due to the viscous shear is given by product of shear stress and surface area. So del fs we can write 2 pi r del L, so 2 pi r into del L into tau, so that is the viscous shear force. So here 2 pi r dl is the surface area of the cylindrical surface of the fluid element, and we already know that concentric cylindrical fluid element with radius r and length del x within the pipe as shown in the above. Now according to Newton's second law of motion in the radial direction, so according to the Newton's second law of motion, we can write summation of that all this radial force is equal to ma, so that is equal to 0. So all this force, so one force is left hand side pi p into pi r square minus as opposite side, so p plus del p into pi r square, and that shear viscous shear force also act opposite direction of fluid flow, so that is minus sign. So minus 2 pi r del L into tau is equal to ma. Now here as the flow is steady, so acceleration is 0, so ma is 0. So we have this equation. Now as the flow is steady, laminar and uniform, the total acceleration is 0. According to the Newton's second law of motion, the summation of all forces in the direction of the flow is equal to the product of mass and acceleration, and the summation of all forces in the direction of the flow must be 0. So acceleration is 0. So now we have that p pi r square minus p pi r square minus del p pi r square minus 2 pi r del L into tau, that is equal to 0. Now here that pi r square and pi r square will be cancel out, so we have minus del p pi r square minus 2 pi r L del L dot tau is equal to 0. Now that is we have, and now here, so pi will be cancel out, 1 r will be here. Okay, so now if we do that simplification, we will have minus del p r minus 2 del and dot tau is equal to 0. Now if we reorganize, so minus del p by del L minus 2 tau by r is equal to 0. So finally if del L tends to 0, so we'll get dp by dl plus 2 tau by r is equal to 0. So we get that one equation. Now so we know that dp by del L plus 2 tau by r is equal to 0. Now this equation illustrates the distribution of shear stress across the flow section. The pressure gradient del p del x depends on solely on the flow direction, that is in x direction. Therefore, the equation above establishes a linear relationship between the shear stress and radius r, and it appears from the equation that shear stress is maximum at the pipe surface. Shear stress is maximum at the pipe surface. Now, if we put boundary condition r is equal to capital R, so we will get del p by del L plus 2 tau w r is equal to 0, and 0 at the center of the pipe where r is equal to 0. At r is equal to 0, tau is equal to 0. So r is equal to r, tau is max. Okay, now if I draw the velocity profile, profile will be parabolic, and what will be the shear stress distribution, that will I'll talk about in the next slide. Now here, so at r is equal to r, del p by del L plus 2 tau by r is equal to 0. We got that. Now here del p by del L is a fixed constant for particular cross sectional area. Now at r is equal to capital R, so del p by del L plus 2 tau w by r will be 0. Now from here, if I from these two equations, we can easily get tau by r is equal to tau w r. Now here tau will be tau w by capital R into r. So this is the straight line equation. So we will get the shear stress distribution. So at r is equal to 0, tau will be 0. At r is equal to capital R, so tau will be maximum, tau max, maximum. That we will get. Now if I draw the velocity profile, so this is the velocity profile, this is the parabolic profile. At the center line, velocity will be maximum, means r is equal to 0, that v is equal to v max, and r is equal to r. At the surface of the pipe, u will be 0. And opposite for this shear stress distribution, at the center the tau is equal to 0 and maximum at the surface of the pipe. So this is the shear stress profile and the velocity profile. So now here, so as we are applying Newton's law of viscosity, so we know that tau is equal to mu du by dy, we know that. And here, so r is always taken from that center line of the pipe from and going towards the surface, and y is always taken from that surface of the pipe to that center line. So we can write y is equal to y r minus r. So now y is equal to r minus r. Now dy is equal to minus dr. So if we change that, so that minus sign will come. So that tau is equal to mu du by dy to minus mu du by dr. Now we also know that tau by r is equal to tau w by r. So from here, tau is equal to tau w capital R into small r. Now here we can plug this tau value. Okay, so tau w capital R by r is equal to mu du by dy. So now we can change dy is equal to minus dr. So for that we will get, so tau w by r into r is equal to minus mu du by dr. Now if we multiply dr and put all together, so we will have this equation. So tau w by mu r, mu will be here, going into small r into dr, minus sign will be here, is equal to du. Now if we do the integration, now integration will be, so just we are reorganize. So integration will be, so for here, so integration that will be u, okay, is equal to, what is that? So that will not be here. Okay, so okay, I can erase that. So that is nothing but something minus tau w mu capital R square by 2 plus constant. So that is already I am giving here. Okay, so I have to erase that. So if we do that, we will get that. So now ultimately, so minus tau w by mu r, so that is minus tau w by mu r square by 2 plus c. So here c is constant. Now we have to find out c. So with boundary condition we know, so at r is equal to capital R, u is equal to 0. So velocity near wall is 0. Now if I put that, so u will be 0 and r will be capital R. So c will be tau w mu r by r square by 2. So that will get the c constant. So finally u is that local velocity. So that is local velocity we can write. So u is the local velocity. So that will be, again we can erase that. So local velocity, so that will be, this is local velocity. So tau w by 2 mu r square, capital R square minus small r square. Now if I put different r value, if I go from here to here, so we will get different u, and we can easily plot that. Okay, so now here we already know that at r is equal to capital letter dp by dl plus 2 tau w I is equal to 0, and it is also a if you plot u versus r, you will get parabolic profile, because this is the parabolic equation. Like that we already showed to you, already given to you, right? So now at r is equal to capital R, dp by dl plus 2 tau w by r is equal to 0. Now if we plug that tau w, so we'll get u is equal to 1 by 4 mu minus dp by dl capital R square minus r square. So we just plug this here. From if we plug this, so 2 tau w will be what? 1 by tau w by r. Tau w by r will be that del p by del l. Okay, so minus and into 1 by 2. So 1 by 2 already here. So 2 by 2, 1 by 4 mu minus dp by dl r capital R square minus r square. So now at r is equal to 0, u is equal to u max. So from here if I put r is equal to 0, we get that u max. U max will be 1 by 4 mu minus del p by del l r square. Okay, and then finally u max will be 1 by 4 mu minus dp by dl capital R square. So that is u max we got. So what will be the maximum velocity at the center line? So that is 1 by 4 mu minus del p by del l into r square. Now volumetric flow rate. So volumetric flow rate is q by pi r square. Okay, so that is that q is equal to v into a. Okay, so that is volumetric flow rate. So q by pi r square, and q is here discharge through pipe, and cross section area of the pipe is pi capital R square. Now consider a small, so here consider a small cross section. Okay, or ring of the element, fluid element, radius r, and thickness is dr as shown figure, right? This is the figure. And so if we calculate the dq inside this ring, okay, so velocity at the radius r and small circular ring element area, so we can easily calculate. So dq is equal to u into 2 pi r into dr. Now if we plug that u, already we know from the previous 1 by 4 mu minus del p by del l r square minus r square into 2 pi r dr. Now, and if net discharge flow through pipe q, so in q will be integration of 0 to r dq. Now we know that q is equal to 0 to r dq. So dq we know here. Okay, so we plug this here. So 0 to capital R 1 by 4 mu minus dp by dl r square minus r square 2 pi r dr. Now q will be, so the constant 1 by 4 mu and 2 pi, that is constant, and taking out minus dp by dl also constant. I told you in particular cross section that dp minus dp by dl is constant. So we have 0 to r square minus r square r dr. Now if we do the integration, or if we reorganize, or if we simplify, so that will be r square small r minus r cube. Now we have to integrate, and if we put that the limit, so that will be q is equal to 2 pi 4 mu minus dp by dl r square into capital R square by 2 minus 4 by 4. So now if I do the simplify, so we'll get this, and if we further simplify, we'll get this. So q will be this pi by 8 mu minus dp by dl r to the power 4. Now average velocity, we know that v in this is average velocity, okay, v into a, so v will be q by a, so that way we q by pi r square. So if we put that, so average velocity will be 1 by 8 mu minus dp by dl and capital R square. So that is average velocity. Now so average velocity is 1 by 8 mu minus dp by dl r square. And u max we already got in that previous slide, so that will be 1 by 4 mu minus dp dl r square. Now if I take the ratio u max by v, so we'll get that 1 by 4 mu minus dp by dl r square, 1 by 8 mu minus dp by dl r square, that will be 2. So u max will be 2 into average velocity, or u max will be 2 into average velocity, or v will be u max by 2. This is very important, we'll get that. So now, so this is again, that is the pipe. Now we are taking one point and 2 the section, so 1 section and 2 section, and diameter of the pipe is d, and velocity, average velocity is v bar. Now if we apply the Bernoulli's equation, so p1 by rho g plus b1 square by 2g plus z1 is equal to p2 by rho g plus v2 square by 2g plus z2 plus hf. If we do that, so now here, that in that section, as it is a steady flow, so now and if it is a horizontal pipe, so z1 is equal to z2 and v1 is equal to v2, means v1 bar is equal to v2. So whatever velocity here, okay, and so that velocity is here, right? So now this will be cancel out, this will be, sorry, not this one will not be cancel out. So this will be cancel out, this will be cancel out, this will be cancel out, and this will be cancel out. Ultimately we will get p1 by rho g is equal to p2 by rho g plus hf. So hf is frictional losses, that is hf. Now so p1 by rho g minus p2 by rho g is equal to hf. Now this is, here is p1 and this is p2. Now p2 minus p1 is nothing but del p, okay. So now that will be del p, so del p by rho g is equal to, so p2 minus p1 is nothing del p, the pressure drop. So that del p by rho g is equal to hf. Now earlier we got that v bar is equal to 1 by 8 mu minus del p by del l r square. So here del p by del l is equal to 8 v bar mu by capital R square. So reorganize, and then p2 minus p1 by del l, so del p is nothing by p2 minus p1 by del l is equal to this. Now from p1 is nothing but, p2 is nothing but p1 minus del p minus p1, so from that we will get del p by del l 8 v mu by r square. And from this del p, and if we take that entire length, okay, so entire length l, so now it will be del p is equal to 8 v bar mu l by r square. Okay, now if we change, so we know r is equal to d by 2. Now if we plug this, so we will get del p is equal to 32 v mu l del square. Now if I divide with rho g, del p by rho g is equal to 32 v mu l rho g d square. So now here del p by rho g is equal to 32 v V mu L rho G d square, that is equal to HF. So this is actually called Hagen-Poiseuille equation. So now here, so if we know the velocity of the pipe, if we know the fluid viscosity, if we know the length of the pipe, if we know the diameter of the pipe, if we know the density of the pipe, we can easily calculate what will be the pressure drop or what will be the frictional losses. So that's why Hagen-Poiseuille equation is very famous to calculate pressure drop. So that's it. Thank you.